What we're going to do is we're going to look at our fourth method of determining the enthalpy change of a reaction. So far we've looked at calorimetry, we've looked at Hess's law, standard enthalpy of formation, and our fourth method is bond energy. Now, we know that inside of the bonds there is a certain amount of energy or potential energy. And so if we know the amount of energy in all the bonds of my product, and I know the amount of energy in all the bonds in my reactants, the difference between those two reactions would be equal to the energy change during my reaction. Okay, so what we can do is we can determine the amount of energy in all of my reactants, determine all of the bond energy, all of the energy in my products, and then use that to determine the energy change. Now, what we have to keep in mind is the way bond energies are expressed. It takes energy to break a bond, so all bond energies are positive values, but when a new bond forms, it releases energy, so it's a negative value. The amount of energy it takes to break a bond between two atoms is the same as the amount of energy released when that bond is formed. So here we have a table listing the bond energy for a number of different elements when they're combined together. And we have both single bonds and multiple bonds. Okay, so we can look at the difference. We have to look at the total, so our enthalpy change is the difference between the total energy required to break all the bonds and total energy released when new bonds are formed. So let's take a look at this. What is the molar enthalpy of combustion for propyne? Okay, so we go through it. So just like for all of our other questions, the first thing we need to do is we need a balanced chemical equation. So I have my equation here. Now, because we're going to be looking at bond energies and the breaking of bonds, we will need to know the bonds that are in each of my compounds. So the next thing I need is the Lewis structure for everything. Now that I know all of the energy associated, or all of the bonds that are present and how the atoms are arranged, I can now look up my given values. And so to do that, the first thing I'll do is I'll count how many bonds of each type I have. So I have one carbon-to-carbon bond here, and I have a carbon-to-carbon triple bond there. And then I have 1, 2, 3, 4 carbon-to-hydrogen bonds. For each oxygen, I have one oxygen-to-oxygen double bond, but in my balanced equation, I have 4 oxygens, so I have 4 of those. Likewise, for each carbon dioxide, I have 2 carbon-to-oxygen double bonds, but because I have 3 carbon dioxide produced, and they each have 2 carbon-oxygen double bonds, I have 6 of those in total. And finally, we end up having 4 hydrogen-to-oxygen bonds. And then I'm going to look up the bond energies for each of them. So now I have my givens. I know the number of each bond type and the energy associated with each bond. So now I can write out my equation, just like we always do. The number of each bond type times the bond energy of each of them in my products minus in my reactants. Or sorry, my reactants minus my products, because this is the energy required to break all of the bonds. This is the energy that's formed. So now I can substitute in my values, and I get that my enthalpy change for this reaction is negative 3,501 kilojoules. Now, because we were asked for the molar enthalpy of combustion, I just have to take this value and divide it by the number of moles in my balanced equation, and we can see here a coefficient of 1.